Good afternoon, Brinhamda, everyone. Welcome to the Open University's Mathematics Christmas Lecture. My name is Vicky Brown. I'm going to be introducing our speaker today. I'm a lecturer at the Open University. I work on mathematical biology, and specifically I use maths to model how infectious diseases spread in populations, which is a topic I love and it's very interesting. So that's me. But as I said, I'm just here to introduce our speaker today, Dr. James Grime. He's a mathematician and a public speaker, and he travels the world giving public talks on the history and mathematics of codes and code breaking. And he's also a presenter of the popular mathematics YouTube channel Numberphile, which I highly recommend if you haven't had a chance to check it out. Well worth a view. So without further ado, I am going to pass over to James for his talk, which I am really looking forward to, and I'm sure you all are too. So thank you very much and welcome, James.
Okay, over to me. So first of all, I want to say hi to everyone. Hello, everyone. Welcome to all the schools that are joining us. Hi. And welcome to everyone on YouTube as well who are joining us. Hi. Let me introduce myself very quickly. So I'm James. And like Vicky said, I usually sort of travel around and give talks about code breaking, which is all good fun because it's all about secrets and spies and espionage and secret messages and things like that. But I'm going to do something slightly different today. So what I'm going to do is similar, but slightly different. I want to talk about how we send messages on the internet. So what I'm going to do is share my slides first of all. And this might be stuff you've heard of before, because when I say how we send messages on the internet, I mean every message that we send on the internet today is transmitted as ones and zeros. So this is something that you might have heard of before. So every message that we transmit on the internet is transmitted as ones and zeros, which means that every tweet on Twitter is transmitted as ones and zeros, right? Every post on Facebook is transmitted as ones and zeros. Every photo on Snapchat is transmitted and stored as ones and zeros, so you can be as beautiful as I am here. So this is what I want to talk about today. I want to talk about the maths and the technology behind how we send these messages on the internet. So we'll go straight into it with our first problem, which is this. So even now in this room, I am surrounded by invisible messages, and they're being sent with radio signals. So there's all these radio signals happening all at the same time, and they're coming from my Wi-Fi, they're coming from my mobile phone, they're coming from the GPS, they're coming from all these things at the same time. And you should imagine these signals like little beeps. It's a little bit like Morse code. You may have seen Morse code before. You might have seen it in old films when you're sending messages with beeps, when you're going beep, 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 beep. So that's Morse code. Imagine it like that. So we have all these radio signals all happening at once, all with like little beeps. And here's the problem. These signals should be interfering with each other. What should happen is when you're using your mobile phone, if you're out and about and you're trying to use, I don't know, your 4G and you're trying to find Google Maps and find where you are, what should happen is all these signals should interfere, and you're sort of constantly sort of straining to get a signal, constantly fighting for it. Yeah, sort of doing a sort of Lion King impression like this, trying to get a signal, but you don't. So why not? So the solution to this problem, well, the solution to this problem has a rather unlikely inventor. The person who came up with an idea to solve this problem with the interfering signals was very famous at the time, but you might not have heard of this person, so I get to tell you about this person instead. So the person who came up with this idea was actually a 1940s Hollywood film actress known as Hedy Lamarr. Here she is. She's a very glamorous woman, as you can tell. She was known as the most beautiful woman in the world. All this is true. You can look her up. She starred in lots of films. Like I said, she was a film actress from the sort of golden age of Hollywood. You can look her up on Wikipedia. And she was also a secret inventor. And Hedy Lamarr here came up with an idea to stop signals from interfering. And that idea we now call frequency hopping, and it's an idea we still use in Wi-Fi today. So I want to show you the gist of how this idea works. So imagine I'm going to send my friend a message. So I've got a friend over there, and I want to send my friend a message. So I'm going to send them with a radio signal, and there might be a bad person, and that bad person wants to block that signal. Okay, so to block a signal, all they have to do is broadcast on the same frequency at a higher power. That blocks the signal. That means my friend will not receive my message. So what I might do instead is decide to use 5 different frequencies. So I might send my message maybe 1 letter at a time using 5 different frequencies. Now my enemy there in the middle can only block 1 signal at a time. That's because it takes power to block a signal. So I can use these 5 different frequencies to get my message across. But there is something I have to do. Me and my friend over there need to share a secret. We share a secret sequence of frequencies that only we know. So very quickly we share this secret sequence of frequencies like that, really fast. There we go, we share a secret. Now we both know the sequence, but my enemy doesn't know the sequence. So now I can start sending my message. Maybe I'll send something simple. I could just say hello, why not, right? Simple message like hello. And I might do that 1 letter at a time. So I might send my first letter, the H there for hello, with frequency 5. Then I do the next letter, E for hello, with frequency 3. And then I can keep going like this. But the idea is that the sequence is unpredictable. So I keep changing the frequencies, but also this sequence is unpredictable, which makes it very difficult for my enemy there, the bad person in the middle, makes it very difficult for them to block the signal, either accidentally or on purpose. So this is the idea of frequency hopping, to rapidly change the frequency. And so this was Hedy Lamarr's idea. Rapidly change the frequency so that signals can't get blocked. She was actually trying to invent a remote control torpedo for World War II. So we're talking about World War II here, and at the time it was possible to make a remote control torpedo. So that means you've got a torpedo that you can fire and you can steer it. So you can steer it and sink ships, great. But then your enemy just has to sort of broadcast on the same frequency. It blocks the signal, you can't control the torpedo, it flies away, no good. So Hedy Lamarr says we should rapidly change the frequency. She didn't just do this by herself, she did this with a friend of hers, a musician called George Antheil, there he is, and he suggested they make it like a self-playing piano. Now, I don't know if you've seen self-playing pianos before. You might have done. Those are the ones that, so they play their own tune. The keys kind of move by themselves. It's kind of ghostly and it plays a tune. If you don't know how they work, inside the self-playing piano, there is a roll of paper. And that roll of paper runs and it tells the piano which note to play and for how long, and it plays a tune. So George said, well, we'll make the torpedo the same way. Inside the torpedo, we'll have a strip of paper. And when you run the strip of paper, it tells the torpedo which frequency to use and for how long. On the ship, you have the same thing, strip of paper that will run. If you fire the torpedo, these 2 strips of paper will run together so that the ship and the torpedo can be constantly changing frequency, but they will remain in sync. And you can control the torpedo, sink ships. It is a very good idea, and they actually took this idea to the US Navy, and in the end the US Navy turned it down. They didn't use it. They didn't use it because they said, how on earth are you going to fit a piano inside a torpedo? Right, completely missing the point. Right, the whole thing could have been shrunk down to the size of a coin if you wanted to. That wasn't the problem, so they didn't use it. But that idea is what we now use in Wi-Fi today. So Wi-Fi, Bluetooth, your phones, your GPS, what you might be doing is that you and the transmitter, if I'm using my phone, say, me and the transmitter will be constantly changing frequencies. So very rapidly changing frequencies. But what that means is that if there's lots of people in my area using their mobile phones, then we can all use the same sort of range of frequencies at the same time, because we're all sort of rapidly changing frequencies and we don't interfere with each other. So that's a really clever idea, and like I said, using all these different technologies. But I did say the messages we're sending are being transmitted as ones and zeros, and I haven't really talked about that yet. So why? Why do we send our messages with ones and zeros? So what they used to do is they used to send messages with waves. So an old-fashioned telephone, right? An old-fashioned telephone used to pretty much work like tin can and string. You probably know when I speak, sound is a wave. So I speak and sound is a wave, and an old-fashioned telephone used to turn a sound wave into an electrical wave and then send that down the telephone line. So the problem with sending sound as a wave is that it gets weaker with distance. Now Morse code was different, and I mentioned Morse code earlier. Morse code didn't send messages with waves like this. It used to send messages with beeps. So I mentioned beep, 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 so that's how Morse code would work. And beeps were clearer. So they're clearer, and you can actually send Morse code messages further. Because they're clearer, they can travel further. So Morse code was slightly better. But Morse code, and by the way, you should think of these beeps, think of these as our ones and zeros. So if a beep is a 1, then think of it as ones and zeros in that way. But Morse code was only used to send text, right? So letters of the alphabet. You don't use Morse code to send sound. Telephone conversations. You don't use Morse codes to send video or pictures or anything like that, music, until they realized that actually, yeah, you can use ones and zeros to send any message you want. It sounds kind of obvious now. You might think, isn't that obvious? Because that's what we do today, because all our messages are sent with ones and zeros today. But at that time, maybe less obvious. Every message can be sent as ones and zeros, including things like photos and sound. But I'm going to give you an idea of how this works. So we're going to send a message. So this is the guy who came up with the idea. This is an American mathematician called Claude Shannon. And Claude Shannon called these ones and zeros binary digits, or bits for short. And he realized not only can you send any message you want, but you can actually send messages efficiently. And by efficiently, I mean short as possible. That would be good, wouldn't it? If I could send my messages and make it as short as possible. You could send messages secretly if you wanted to. That's also good. And you could reduce mistakes. So you could make it so that there are as few mistakes as possible, or even you could fix mistakes if they happen. So these ideas is what I want to talk about next. But okay, let's try and send an easy message using this kind of ones and zeros or binary digits. Now, some of you will know what binary is, but some of you might not know what binary is. If you don't know, I guess binary is just a systematic way of writing numbers using ones and zeros. I'll give you the idea of how it looks. So imagine I want to send someone a message. Maybe it's an email, something like that, a tweet, something text like that. So I'm going to need the letters of the alphabet. Here they are. So that's just A to Z, letters of the alphabet. And when I send an email, my computer turns the letters of the alphabet into numbers. And it actually does that in the simplest way you can imagine. It just sends A as 1, B as 2, and Z as 26. So when you're sending an email, your computer turns the letters into numbers and it transmits that sequence of numbers. That's all your computer is doing, although it does send them as binary numbers. And so the binary numbers look like this. Just to show you what's going on here then, so I just want to point out, they all start the same. So that bit in pink at the beginning, 0, 1, 0, so that's just a little bit of code for your computer. It's telling your computer that this is a letter that you're receiving rather than a number or a symbol or something different. So this is a letter, and then the rest of it That's just 1 to 26 written in binary. It's called ASCII. Here's the whole thing. So that's the whole thing there. We can do an example though. It's not that difficult, I think. So I'm going to put up an example here. So I've got a 3-letter message here for you, and we can use the left-hand side. Let's see if we can find what this says. So the first letter is 010, 00010. Don't know if you can find that. You can shout it out if you find it in your classes. If you can find it, I find is a B. The second letter of this message, 010, 10101. Yeah, again, shout it out when you find it. I think I found it. It's a U. And the third letter of my message, 010, 01101. And I don't know if you can find it. It's an M. I've written bum in binary. It is called ASCII after all. Hey, I just do this for my own entertainment. So it's quite a simple idea. You're turning the letters into numbers and you send those as binary numbers. I wonder though if we can make this more efficient, so shorter. So what we've done here is that each letter that I'm sending uses 8 binary digits, 8 bits. I wonder if we could make this shorter. I mean, I'd give you a second to think. Is there a way that we could make this shorter somehow? So you might be able to think of a way. One way that I can think of straight away is we don't really need that bit in pink there, the 010 bit. So that's just a little bit of code, but we can just send these letters using the 5 binary digits, the actual binary numbers themselves. So we could make this shorter. So instead of being 8 digits for each letter, it could be 5 digits. Could we make it even more efficient though? Is there another way to make this more efficient, to make these messages shorter? So there is a way to do this as well, and it requires us to think about the most common letters in English or whatever language that you're using. So what are the most common letters in English? In fact, we can do this. I mean, you can shout them out in your classes. Does anyone know what the most common letter in English is? Do shout it out if you want to. What is the most common letter in English? I will tell you, and it's probably not a surprise, the most common letter in English is E. Does anyone know what the second most common letter in English is? You can try and shout that out as well. Second most common letter in English. I will tell you, I think this is a bit surprising. Second most common letter in English is T, which you might not expect. So E is number 1, T is second, A is third, and so on and so on and so on, which you might expect. Then you have the vowels. What about the other end of that scale? What about the rare letters? Do we know what the rare letters are? Could you shout out some rare letters? What could be a rare letter in English? So you might have a Z, you could have X, you could have a Q maybe. Let's have a look. Here comes the graph. This is showing you the common letters in English in order. Let's have a look. So it's E as the most common letter in English, and then you've got T and A, and you've got the vowels there, and then, well, as you might expect, things like X, Q, Z. J is a rare letter. I think that's a surprise. J, I'm a James myself, but J is a rare letter. But we can use this to make our messages more efficient or shorter. What we're going to do is we're going to send the most common letters with shorter code words. That's that little sequence of 1s and 0s. It looks like this. So we've got the most common letters, your E, T, and A, using shorter code words, and you've got the rare letters at the other end of that using much longer code words. But what that means is that on average, your messages are shorter because you're using the more common letters more often. Your letters are more short on average. I'll give you an example of how this might work. With an easy example, I'll do an easy word that's like a really common word, right? Really common word. So you might be using that a lot. And if we do this using this code, it's called a Huffman code if you want to look it up. Huffman code. So it's a way to make these messages as efficient as you can. It looks like this. So we've got T here with 4 digits, H with 4 digits, and E with 3 digits. And so this is now much shorter than sending it with just binary. But this is actually as efficient as you can be if you're just doing this one letter at a time. You can be more efficient if you looked at pairs of letters. What you could do instead is take your message, maybe your email, and break it up into pairs of letters. Then you look for the most common pairs of letters and make those shorter code words. That would be even more efficient. Or if you want to be more efficient again, you could break it up into triplets. So if you break up your message into triplets, look for the most common triplets and make those shorter code words. That would be more efficient again. So it gets more efficient if you break it up into larger blocks. So that is a nice way of making your messages shorter if you want to. And this idea isn't just for text messages like your emails. This idea can be used for anything. You can use this for your photos, your videos, your music, whatever. So if I was sending a photo on the internet, you might know this, right? These digital photos, they're broken up into pixels. You might have heard of that. So your digital photo is broken up into pixels, and that is given a color, and that color is given a number. So your photograph is just a sequence of numbers, which can be sent as a sequence of binary numbers. Fine, and then it's ones and zeros. Or you can make it more efficient and you actually look for the most common colors. Look for the most common colors, give those shorter code words, and it will be more efficient. Same for video, like this video call that I am on right now. It is probably working exactly the same way. They're looking for the most common colors in my background, probably looking to remove some unnecessary details so that they can make this transmission, which is ones and zeros, as efficient as possible. Another nice thing about this is it can be different for different messages. If you can actually write an email, your computer can then scan that email and actually base a code on the frequency of the letters in that particular email. So it can be different for different emails. Every message could be different. So to make it as efficient as possible. It's a lovely idea. But this is how we could be sending our messages like with our ones and zeros. But I want to talk about how we could send some secret messages. Maybe that's something you would like to do. How could we send messages secretly? There's a few ways you could do this, but I want to tell you this one, which goes back to World War II again. It's another World War II story, and this is an idea that was used by Nazi Germany in World War II to send their secret messages. So the idea is, you can imagine in a war, like it's World War II, you're going to have secrets that you want to keep. You don't want your enemies to find out your secret plans. You're going to send your secrets in code. And Nazi Germany had a code machine that they thought was unbreakable. If the Allies can break that code, I mean the Americans, the British, can they break that code? They can read all those German secrets, which is going to help a lot. And that's exactly what happened. I don't know if anyone knows which code I'm talking about. You might have heard of this before. You might have heard of the Enigma machine before. Yeah, maybe. You might have heard of Enigma. Because it's quite famous now, Enigma. So this is the Enigma machine. It looks like a typewriter. There's 3 wheels inside that typewriter. There's some wires at the front, if you can see on that photo. Some wires. It's all part of the code. So if you change those wheels, if you change those wires around, if you move them around, it all changes the code. You might have heard of that Polish code breakers broke the code first before World War II. You might have heard the British code breakers were breaking it in the war. You might have heard of Alan Turing. He's quite famous. So he was a famous mathematician, broke Enigma codes in World War II. You might have seen the film. Benedict Cumberbatch was Alan Turing a few years ago, breaking codes in World War II. Here's the thing though, I'm not talking about Enigma today. No, I'm not. No, that's the famous one. Okay, so this is the machine that people know. This is the story that people know now. There was another code machine that Nazi Germany were using in World War II, which was even harder than Enigma. It was worse, even worse than Enigma. And that machine was called Lorenz. This is the Lorenz machine. It had 12 wheels in the machine, so it was a bigger machine, even worse code, and this machine was used by the top level of the Nazi Party for the most secret messages, used by the top generals, including Adolf Hitler himself. That's a kettle that looks like Adolf Hitler, by the way. I know that takes a moment, so I can't wait. Yeah. Oh yeah, it is a kettle that looks like Adolf Hitler. Yeah, I know it is. So this is a code used by the top level of the Nazi Party. And I want to show you how this code works. And it works by sending messages with ones and zeros, kind of like the internet. Although in World War II, they didn't used to call it ones and zeros. They used to call it dots and crosses. So I want to play this like it's World War II. So we're going to use dots and crosses. It's the same idea. So imagine now I'm going to send a message. I'm just going to send a letter M for message. And I'm using this in this code. M becomes dot, dot, cross, cross, cross. Now, if I transmit that message, there's nothing secret about this. This is well known. So if someone intercepts that message, they would get dot, dot, cross, cross, cross. That's the letter M. So that's not secret. If you want to send it secretly, you would have your Lorenz machine. And your Lorenz machine would generate a random letter. Random, I say random, it's a fake kind of random, but let's say random. So it's an R for random. So in this example, it's created a little sequence of dots and crosses. Dot, cross, dot, cross, dot. We've now made 5 pairs of symbols. Hopefully you can see the idea. I've got 5 pairs of symbols there, and we're going to add those symbols in pairs to make our code. And the rule is, if the 2 symbols are the same, they make a dot. If the 2 symbols are different, they make a cross. So let's see if we can work out what this code is. You can shout these out as we go through them. So I'm going to do the first pair first. So I've got a dot plus a dot. And in this code, they are the same. That makes a dot. Second pair, dot plus a cross. They are different. So in this code, it makes a cross. Third pair, cross and a dot. They are different. So this code says it's a cross. Fourth pair, cross and a cross. They are the same. So it's a dot. And in the fifth pair, cross and a dot are different. So that makes a cross. That's the code you get. Dot, cross, cross, dot, cross. In this code, that's the letter P. So you'll be transmitting the letter P. So you would transmit that away. And then somewhere far away, you have your second German officer. And they're receiving this coded message. So they've got this letter P, okay? They would have a second Lorenz machine. So they've got a Lorenz machine as well. And their Lorenz machine is set up exactly the same way as the first one. So all the wheels are in the same position. It's all set up exactly the same. If you set it up exactly the same, it will create the same random letter. So it isn't really random at all, but it creates the same letter as we had before. I'm going to get the letter R again. Now I'm going to add that to my code in pairs, just like before, to get my final message. And if you're ahead of me, you might be able to see what's going to happen. This is what I'm going to get. Dot, dot, cross, cross, cross. And that is the letter M again. So I get my original message back. So the idea is, you've got your German officer typing a message. You've got your Lorenz machine creating random dots and crosses. That's added to the original messages in pairs. Pairs of symbols are added together, creates a code. Send the code. Then you've got your second officer. They're receiving the code. They create the same sequence of dots and crosses. So the same sequence of random letters with their machine. And that will cancel itself out. And you will get the original message back again. That's the idea. This is an incredibly hard code to break. I've actually got a little bit of video here, which should work. And just to show you how it works, this is one of the few Lorenz machines left in the world. I think there's 4. I think there's 4 of these left in the world. They're really rare. So there's 12 wheels. And as you can see, every time I type a letter, those wheels are moving And when they move, they are creating a different random letter. They're creating a different sequence of dots and crosses, and those wheels are moving in a kind of unpredictable way. So that code is changing for each letter of your message. So it's a really hard code to break as well. So there's that randomization in it, and it's kind of unpredictable the way it moves as well. And I want to show you how hard this is to break. So the Enigma machine, the famous one, the one that everyone now knows about, Enigma machines, was a hard code to break. Like I said before, it has 3 wheels, which actually you can swap over, you can change their position. At the front, there are some wires that you can move around. That's all part of the code. And every morning, you could change how to set up the Enigma machine. So every day, you could change the settings, and the number of total possibilities was a large number. It was this number, 159 million possibilities. And so number of ways you can set the Enigma machine, huge number, right? Far too many to check. There are more possible Enigma settings than there are grains of sand on Earth. That's how big that number is. It's a ridiculous number. But Lorenz was even worse. We compare it with Lorenz. So Lorenz had 12 wheels, and you can't really see on this photo, but on the outside of the wheels, they have little on-off switches. Those on-off switches are creating the dots and crosses. And then those wheels are moving in that unpredictable pattern as it goes along. Now, the number of ways of setting the wheels and the little on-off switches that are on those wheels is another large number. Total ways of setting Lorenz, and again, change it every day, is this number. Right, and I'll try and say this for you. It's going to be 100 million, 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 million. I run out of breath, I pass out. Okay, so huge number. That number is actually 170 zeros. Absolutely massive number. More than there are grains of sand on Earth. In fact, there are more Lorenz settings than there are atoms in the observable universe. Absolutely ridiculous number. Far too many to check. In fact, it's even worse than that, because if each atom in the observable universe was itself a universe, there would be more Lorenz settings than there are atoms in a universe of universes of atoms. It's just a ridiculous number. So hopefully you can see why the Germans were proud of this machine. Absolutely brilliant machine. Far too many possibilities to check, and the way it's always changing. That's important too. So it's always changing as you type in your message. So you're always getting different random letters as you go along. So really hard code to break. Although we did break it, and this is where we did it, a place called Bletchley Park, which you may have heard of. That's a famous place now. It's a museum now, if you want to go and visit. It's just outside Milton Keynes, so you can go visit this place if you want. They'll tell you all about how they broke Enigma codes in World War II. They'll tell you all about how they broke the Lorenz code in World War II as well. At the time, it was full of very clever people. So these code breakers, some of them were mathematicians like myself, but not all of them. Some of them were engineers, some of them were linguists. Languages is a similar skill to code breaking. So if you're good at languages, that's something they needed. Some of the people who worked at Bletchley Park were just people who were good at puzzles and games. That's exactly the sort of thinking they needed to break these codes. Now, to begin with, they were receiving these Lorenz messages, and they had no idea how the code worked. They had never seen the machine. They didn't know how to break it. They didn't know how it worked. Until one day, there was one fatal mistake that helped them break the code. So I'll tell you what happened. One day, a German officer was using Lorenz to send a message, quite a long message, using Lorenz to send a message, and he sent the message away, but the person at the other end didn't receive the message. So that person had to send a message back saying, "What? Hey, pardon, could you send that again, please?" The first person was so annoyed that they had to send this message again. They reset their Lorenz machine, started to send the message again, but this time they started to send it with a few abbreviations, just to make it a little bit shorter and easier to send. But what that meant was that at Bletchley Park, they had 2 copies of the same message in code that were slightly different. And from those 2 codes alone, they were able to completely reverse engineer the machine that made it, which is amazing you can do that. Remember, without ever seeing the machine. What they did, they took those 2 codes, and those 2 codes were made with the same key, the same random letters. So they added the 2 codes together, pair by pair, and the key cancelled itself out. And the result was the 2 original messages added together. And then it was a linguist who then slowly, over a period of 10 days, started to sort of pull apart those 2 original messages. And so he could get the original message. In fact, that was a code breaker who was an experienced code breaker from World War I, used to be a code breaker in World War I, was a code breaker or a lead code breaker in World War II. Like I said, it took him 10 days to do. The message he got wasn't that interesting, actually. But what he could also do is he could also work out the random string of letters made by the Lorenz machine. So the random dots and crosses. And he gave that random string of dots and crosses to a young mathematician called Bill Tutt. There's Bill Tutt. He was fresh out of university, just graduated, and he had a reputation as being a bit of a puzzle solver, a problem solver. So they said, here, take these dots and crosses. What do you think? And there are stories of him staring off into space, and the other code breakers are sort of looking across the room thinking, what's Bill even doing over there? Is he working? He just seems to be staring off into space. Yes, I am working. I'm thinking about it. And eventually he noticed a pattern. There was a pattern in the dots and crosses. And using that pattern, he could then start to work out how the machine worked. And then the other code breakers, they started helping out, finding these little patterns. They completely reverse engineered the machine, and they could build their own, again, without ever seeing it. Lovely stuff. Although having the machine is only half the problem, because you've got the machine, but the other half of the problem is, what position are the wheels in today? Because that can change every day. The position of the wheels, that is something you would have to work out. So Bill did have a method for working out the wheel position as well, although his method was a bit hard. It was way too hard to do with pen and pencil. It would be nice if you could build a machine that could do the method for you. And that's when they contacted an engineer called Tommy Flowers. So what's nice about this story is it's this lovely collaboration between these different subjects. You've got your linguist, your mathematician, and your engineer working together. And this would not have been solved without these 3 people working together. And it was actually Tommy Flowers then who designed and built a code-breaking machine. And he designed this thing. It's called Colossus. Colossus because it was huge. Big code-breaking machine, arguably the world's first digital computer. I said arguably there because people argue about this kind of stuff. There are about 11 candidates for the world's first computer, and this is one of them. But if that's true, then we can say the world's first digital computer was built in secret at Bletchley Park to break Hitler's code. And we can actually break messages from Adolf Hitler himself, like literally signed by Adolf Hitler. Fantastic stuff. I love this. There is a reason why I tell this story. Well, partly because it's cool, partly because I want to make this more famous as well. I think this story should be more famous, but the other reason for telling this story is because this is kind of how Wi-Fi works today. So I talked about all the messages we send on the internet are transmitted as ones and zeros. So that could be your photos or your emails. So when you're sending a message with ones and zeros, it might look like this. This is your data. And then what your computer does, or your phone, is it will then generate a random string of ones and zeros. And it will do that very rapidly as well. 1 0 1 0 1 1 1 0 0, like this. it will then add those symbols together in pairs, just like Lorenz worked, and it will make a code. It will look like this. So your messages are being transmitted in code, which is nice. So it's nice and secret. But the other reason they do this is because when you turn that code into a radio signal, it means the signals don't interfere with each other. This is kind of a more modern version of frequency hopping, which is what I started with. So I talked about frequency hopping, and the idea there was the signals don't interfere with each other if you rapidly change the frequency. And this is the same thing. Here, the signals don't interfere with each other if you rapidly change the data. It has the same effect. And both ideas are used for different situations. So if I'm using Bluetooth, like Bluetooth earphones, something like that, that's probably using frequency hopping. But if I'm talking to my Wi-Fi, my internet Wi-Fi, that's probably using this idea, spread spectrum. So both ideas are used. So that kind of solves a problem of interfering signals. But what about if something does go wrong? So this is what I want to talk about next. What about if I'm sending a message and something does go wrong because it can, right? Something can go wrong by accident, right, by mistake. Now, I want to show you this, and this is the last part of my talk. This is what I want to show you, how we can fix mistakes when they happen. But it might be a good time to remind you that if you want to send in a question, when at the end of this talk, which will be in about 8 minutes, we will do some questions and answers at the end. So if you've got some questions for me, maybe it's something you didn't understand, maybe something you want to know more about. If you've got any sort of questions for me, pass them to your teacher so your teacher can put them in the chat. If you're on the YouTube, do put those in the chat as well, and we'll collate them and we'll do those as well, including questions about this last little section here, which is about how we fix mistakes. So what I want to do first is give you the gist of the idea with a little thing that I kind of found on the internet, so maybe you've seen it before, but it's a lovely idea. I'm going to show you a bit of text, and there's going to be mistakes in this text, but I think we can fix the mistakes. So let's have a look at this. So it looks like this. So we've got some text here, and I think we can fix these mistakes. So I'm going to read this out, and you can actually follow along with me if you want. So you could read this out loud too. So let me start. According to research, the position of outside letters in words is more important than the middle letters. This is because the human mind does not just read every letter by itself, but also the words and sentence as a whole. So first of all, can you read that message? Yes, I think so, right? So like it says here, when we're reading a message like that, we are not just like some sort of robot reading each letter one at a time. Our brain is kind of scanning the word, scanning the sentence, and it has to make sense. It has to make sense in context. And our brain can automatically fix the mistake so we can read that message. Well, your computers do the same thing, and they're designed to do the same thing. So let's say I'm sending a message with my ones and zeros with my computer. It might look like that. So some sort of message, and it's all in binary and ones and zeros. So it's looking like this, but there might be a mistake when I send it. So for example, maybe a 0 becomes a 1, like that, there, which I've highlighted in yellow. So a 0 becomes a 1, or maybe it's a 1 that becomes a 0 instead. So I've just done this as an example, but we can fix mistakes when they happen because the actual message that I'm sending is this top left square here. That's the actual message, but I've added an extra row and an extra column, and I've done that for a reason, so that every row has an even number of ones and every column has an even number of ones. If I go to the original message, it looked like this. Let's just check that. Every row should be even. First row has an even number of ones. Second row, it's even. Third row is even. And we can look at the columns. The first column is even. Second column is even. Third column, even if it's zeros, is even as well. Every column is even. But that helps me find mistakes. So imagine now there is a mistake like this. I can find that mistake. I can tell it's a mistake because if I look at the second row, it's odd. It shouldn't be. It's odd and it shouldn't be. The second column is odd and it shouldn't be, which helps me pinpoint the mistake. There must be a mistake somewhere, and I think it's there, the second row and the second column, and then I can fix that mistake so I can get the original message back. This method is a method of fixing one mistake, but there are more sophisticated mathematical methods that can fix more than one mistake. And in fact, even NASA uses these kind of ideas to fix mistakes when they're transmitting images from space. So this is an image of Mars. So this is a photo of Mars. So it's come all the way from Mars. If you can imagine, if I take a photo, all those little pixels that that photo is made from are turned into numbers, which are transmitted as binary numbers. And I've actually included some extra digits in there so I can fix mistakes. So it travels all the way from Mars as a radio signal, and that's a long way. So when it gets to Earth, some of the digits have gone wrong. Some of the ones are zeros and some of the zeros are ones now, and it's kind of come back grainy. But because I've included those little extra ones and zeros in there, I can now correct this image. I can clean it up so it looks like this instead. Hashtag no filter. Hashtag error correction. Hashtag blessed. So it looks like this instead, and you can get a beautiful image on Earth. That idea and the maths that NASA uses to clean up an image like that, it's exactly the same maths that they also use in something like a CD. If you remember CDs, do you remember CDs? CDs, if you zoom in on a CD, your music is saved as sequence of numbers again. Those numbers are saved as binary numbers, but those binary digits or those ones and zeros are saved on the CD kind of like Morse code, kind of like sort of dots and dashes like that. So that is music being saved as ones and zeros physically on a CD. Same for DVD or Blu-ray. So the video is saved as ones and zeros on your DVD like that. But it also includes those extra digits. And those extra digits can then be used. So if your CD is scratched or gets dirty, then you can actually fix those mistakes and the CD can still play. In fact, you can go further than that. You can literally actually drill a hole in a CD. You can actually take out physically part of the song, drill a hole in the CD, and the CD can still play. Amazing stuff. I've always wanted to try it, so that's what I did. So I've actually tried this myself at home. So I want to actually show you me trying this at home. So I've got a video of me doing this at home. So this is a video clip of me, and this is me in my garage. And I have got here, everyone, a CD. So I have a CD here, and this is a Justin Bieber album. It's actually My World. It's his first album. And I have my CD. I have a vise, and I have a drill. I also have safety. So I'm safe and I'm stylish. So I'm going to now drill a hole in this CD. And I'm drilling a hole into track 1. Track 1 is there near the center of the CD. And that is track 1 that I am destroying there. And the hole is not very big. It's a 2mm hole. Doesn't sound very big, but that's a lot of scratches. There is a limit to this. It's not magic. 2mm is your limit there, but that would be a lot of scratches. Now, I place it into my good old-fashioned ghetto blaster, and I'm waiting for it to recognize the CD, and I'm nervous. It works. I'm absolutely delighted. It actually works. I am so delighted I broke out into a dance because it does actually work. That is something you could try for yourself, by the way. I'll go back to my slide. That is something you can try for yourself. I'm not telling you to drill holes. Don't get me in trouble. Don't drill holes in your CDs. But you could do it with a black felt tip pen if you want. Works the same way. Do a little dot with a black felt tip pen. It means the laser can't read what's underneath there. So it has the same effect. And you can try that in a little experiment yourself as well. But I want to finish with this, which is a kind of a quote from the hero from the start of my talk, which was Hedy Lamarr, who said, films, she was a very famous film actress, but she said films have their certain place in a certain time period. But technology, and I'm going to add maths to that as well, technology and maths is forever. I hope you've seen something new. I hope you've seen something different. I'm going to leave it there for now. I'm going to pass it back over to Vicky. I'll give you a moment to breathe, but also we're going to do some questions.
Thank you very much, James. That was absolutely fantastic. I really enjoyed that, and I'm sure everyone did as well. As I mentioned at the beginning, you can't put your microphones on, so we can't give James a round of applause, unfortunately. But do please feel free to add.
You can just do it anyway. Just give your teachers a round of applause. Give your teachers can take a bow for me on my behalf. Yay! Well done. Take all the credit, teachers.
So that was brilliant. Thank you so much. So we've got a few questions that have come in. So I will just pull them up if that's okay. So yes. The first question I've got here is, does the code breaking using binary go back further than World War II, or was it Alan Turing who started it?
Okay, right. Yeah, yes. So it does go back further. Well, you know, it doesn't go back as far as you think it goes back. I know there are versions of this sort of binary code that goes back to maybe 1700s. There is a code called Bacon cipher, discovered by Francis Bacon, who used this kind of idea of ones and zeros to send secret messages. But then this sort of binary stuff didn't really get going until 1800s, and then really this all came sort of into fruition because of computers. So we're talking about World War II era when computers started happening, because electronic relays are on or off, which uses ones and zeros, and then binary became suddenly massively useful.
That's brilliant. Thank you. Just check we're still doing all right for time. So we've got time for a couple more questions. Yeah. So this is another one that's come in. If it has taken us 100 years to get to where we are now, where do you think we'll be with coding in the next 100 years, as we're such a digital focused society?
Right. Well, I guess if you're talking about secret codes, maybe you meant secret codes. If we're talking about secret codes, then the best secret codes we have now is something called quantum cryptography. And the idea there is, if you remember how Lorenz worked, it created a random, but it was kind of fake random, a random string of dots and crosses, or ones and zeros. If you can have a genuinely random sequence, like tossing a coin, of ones and zeros, then that would have made an unbreakable code, actually mathematically unbreakable. So that's great. But the problem then is you've got a random sequence, and my friend over there needs to have that sequence as well. So if I can now transmit that sequence so it can't be stolen, and that's the problem we've got. So this quantum idea is to send the sequence of ones and zeros using particles of light down a fiber optic cable. If a spy has a bit of a spy on it and does a bit of a spy, and then by observing particles of light you change them, then we can detect that and we can shut it down. We can detect it's been spied on. So we can actually transmit these random ones and zeros, and then that can be used for proper unbreakable codes. And this all exists. This is happening. This has existed now, really existed for 15 years, although there are technical problems about how far you can transmit down the fiber optic cables, actual physical distance problems. But it does exist, and we're trying to get it better.
Fantastic, thank you. All right, another one that's come in said, what is the most efficient way for a mathematician who doesn't know much about coding to do pattern recognition using machine learning?
Okay, machine learning is not something I know a lot about, so I won't give you a very good answer for this. But how could as far as I know, so I know nothing, is machine learning is the machine sort of learning from its mistakes, getting better, sort of disregarding the wrong answers, reinforcing the correct answers. I don't know much about it, so I can't answer it, although I do know, because I know a lot about Alan Turing, who I mentioned, this was always something that he anticipated happening one day when we were able to teach the computers to learn for themselves. That was always his dream, and now that is actually happening now. Although, again, it's not something I know much about.
Brilliant, thank you. Another one we've had come in asks, how did you learn to be so confident and enthusiastic while delivering a presentation?
Oh, what a lovely question. How did I learn to be so confident and enthusiastic when delivering math lectures? Now, I guess because I am enthusiastic. I'm very keen to tell you what this is all about because I think it's cool. I genuinely think it's cool. I'm not pretending, and I want to tell you about it. And all I want to do is just show you that I think it's cool. You might not be interested in it, you might not think it's cool. I want you to believe that I think it's cool.
Oh, that's great, thank you. I think we've got time maybe for one or two more, so which is good because that fits in with what I have on my list. So another one I have here is, you mentioned Bill Tutt earlier. What pattern did he see and how did he spot it? This
is a good question. So yes, Bill Tutt, what was the pattern that he saw? So actually, so he took that random string of dots and crosses that he was given, and what he did is he tried a few things, and he experimented with it, and a lot of those things didn't work, and I'm sure he played around with it for a while. In the end, he wrote out the sequence in rows of 43. So he wrote out the sequence in rows of 43, and he noticed a slight pattern in the rows. So every 43rd symbol, there was a slight pattern to it, and what he decided was that meant that one of the wheels inside Lorenz had a period of 43. So it went click, 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 click until it was 43 and then back to the beginning again. So it told you the size of the wheel that was in the machine. And with the other code breakers, they could do the same sort of ideas, and they found other patterns like that. So they could work out how big these wheels were. They were all different. Some were wheels of size 23, some were wheels of size 29, and so on. And then they could build their own copy of Lorenz. Brilliant stuff.
Excellent, thank you. One fun one we've had come in. Which is your favourite Hedy Lamarr film?
Oh, well, I don't know. So there's a lot of those films, and some of those films are a little bit sexist these days. They're all about, this is exotic objects. So there are some films that I wouldn't recommend in a sort of 2021 kind of way. Although some of those films are excellent as well. I think Ziegler Gill is one of the most popular ones.
Brilliant, thank you. I think just one final question now, just before we finish. Just a nice one to end on. Are there any coding developments that you find very exciting that are happening at the moment?
Coding developments that are exciting at the moment. So I did my little speech about quantum cryptography. The other interesting kind of buzzword that I could mention is quantum computing. And that is a different kind of computing than we use now. And that would allow us to factorize large numbers faster than we can already. Now, why is that important? Why do we care about that? Because the codes that we use today on the internet, if you're buying on Amazon and eBay, when you're sending credit card information on the internet, uses factors of large numbers. So it's very important in how we send messages today. If we can factorize large numbers, we can break all those codes that we're sending today. That will be more possible with quantum computing, but that doesn't exist yet. I know that we're getting there, and there's some versions that are getting close to it, but they're really kind of small and tiny, not quite there yet, so we're not in trouble yet. And when those machines do exist, we do have ideas that we can use instead. So don't worry, everything's fine. We will have something that replaces what we use today.
That's brilliant, and that brings us perfectly to the end of our hour. So it just remains me to say thank you again, James. That was absolutely brilliant. I really enjoyed that, and I'm sure everyone joining us did. And thank you to everyone who's joined us. I hope you've had a great afternoon. And thank you and goodbye, everyone.
Bye, everyone.